Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part 2 of the energy storage segment. In part 2 we will conclude the electrostatic and chemical energy storage chapter and discuss hydrogen storage and fuel cells.
It is very convenient to store electrical energy in batteries or capacitors, but the great disadvantage of these storage media is their low energy density per weight and volume. This makes it difficult to build cars or airplanes using electrical motors. Hydrogen offers a way out of this dilemma because hydrogen has a very high energy density and it can be generated from electrical current directly via electrolysis. Once hydrogen is available, it can be burned in standard combustion engines, but it can also be used to make electricity directly through fuel cells. Disadvantages of hydrogen include that it can be very costly and impractical to store it, and also the energy efficient conversion of electrical energy to hydrogen is a challenge. The great advantage of hydrogen as energy carrier is that it can be generated via simple electrolysis of water. So if you have electricity and water and a couple electrodes, then you can produce hydrogen gas and you have a chemical fuel, and this distinguishes it from all other chemical fuels. If you wanted to make methane or something of that sort, it gets much more complicated. The other great advantage of hydrogen is its high energy density. That comes from the fact that when hydrogen and oxygen react to water, a lot of energy is released. We see this here in the energy diagram of this reaction. The electrons on the hydrogen and the oxygen are at a fairly high energy level, and once they react to water, they drop a lot on the energy scale. And so this energy is what's released as heat once the water has been formed from oxygen and hydrogen. Now, when we use electrolysis, we essentially restore this energy into hydrogen molecules, and so we get a fuel that has a fairly high energy per molecule. This picture shows Hofmann's voltammeter. It's a simple electrolysis device that was originally used by Hofmann as a amp meter because the amount of hydrogen and oxygen that is produced in this device is proportional to the electrical current that goes through the circuit. So how does this work? We have two electrodes embedded into this setup, an anode and a cathode. The anode is connected to the positive end of a power supply and the cathode to the negative pole. As the power supply shovels electrons to the cathode on the anode, water is being split into oxygen gas that bubbles out here to the top, and 4 protons, and these protons now they go over here to the negative cathode, right? They're positively charged, and we got also 4 electrons, and these electrons are pushed over here by the power supply. So this is where the energy comes into the system from the power supply. At the cathode then, the protons meet with the electrons and they form hydrogen, and this hydrogen bubbles out on this end and we get it up here. And of course, if we let this run for some time, we get twice as much hydrogen molecules than oxygen molecules, because in water we have 2 hydrogens per oxygen. So it's obvious that the energy in the electrical current that comes out of the power supply is converted into chemical energy that we have in the hydrogen that is stored inside this electrolysis setup. Therefore, this can be used as energy storage if one wants to store electrical energy. The electrolysis process can be reversed, so we can take the oxygen and the hydrogen and we can convert it back into an electrical current. This was first demonstrated by William Grove in 1839, and he essentially took 5 electrolysis setups and 4 of them he connected in series, and he pre-filled them with oxygen and hydrogen. The 5th one he connected to the setup without any gas present, and over time he observed that the oxygen and the hydrogen was reduced in volume in those 4 cells, while here in this 5th cell oxygen and hydrogen developed. This demonstrated that oxygen and hydrogen react to water under release of an electrical current. The exact same principle is used in a modern fuel cell, but in a modern fuel cell the wet electrolyte is usually replaced with a solid-state electrolyte, and when I say electrolyte then it simply means that this is an insulating material that permits an ion current, that permits the hydrogen ions, the protons, from one electrode to the other. Remember, that was what happened in Hofmann's apparatus inside the electrolyte. And so in a modern fuel cell we simply put hydrogen fuel in on one side, and we have this porous anode that extracts the electrons, and the electrons, they flow through the load and they go over to the cathode, and there the electrons recombine with the protons and the oxygen that is coming from the atmosphere, and water is generated, which is output from that fuel cell. So if you look at the chemical reactions, we have exactly the same reactions in the setup, and the only difference is really that we have this solid electrolyte that is typically a ion permeable foil of some polymer that is sandwiched between the anode and the cathode. Let's consider the power output and the efficiency of fuel cells. The theoretical conversion efficiency is about 60%. The remaining energy goes into heat and water evaporation. The current technology delivers about 40%. So if you consider this in light of the 70% efficiency at which hydrogen can be produced on an industrial scale via electrolysis, we get about 28% storage efficiency of the entire process, right? If we multiply 0.4 with 0.7, we get 0.28. Now, the 28% does not take into account that it costs energy to store the hydrogen, because one has to either put it under pressure or cool it down to low temperatures. Both processes can cost about half of the energy that is in the hydrogen that is being stored. So if you compare this with batteries to store electrical energy, this is rather poor. Batteries can achieve 80% or so. So clearly, if one considers hydrogen to store electrical energy, the high energy density is more of interest than the storage efficiency, because that is where batteries are lacking. They're very heavy and they contain little energy per weight, while hydrogen has a lot of energy per weight. So if you want to have an airplane that runs on electricity, then hydrogen is the much better choice. But we need to keep in mind that a lot of energy is lost when using hydrogen. Now in this graph we see a current voltage curve of a hydrogen fuel cell. We also have a power curve. So we see that, like in solar cells, we have a certain current and voltage combination where we can get the most power out of a fuel cell, where it runs most efficiently. So like with solar cells, we have to match a fuel cell with the load. So that makes it complicated to operate a car, for example, where the load changes all the time while we accelerate, or while we're coasting or driving up a mountain or down a mountain. Fuel cells typically need to be combined with capacitors or batteries if they are supposed to run efficiently. There are a number of different fuel cell types depending on the application. Here's a table of some of the important ones. They are mainly distinguished by their operating temperature, by their fuel type, and by the electrolyte that performs the ion transfer between the electrodes. There are cells that have solid-state electrolytes, like polymer electrolyte membrane fuel cells, and then other fuel cells use liquid electrolytes. When it comes to the fuel cells, of course, like hydrogen, but there are fuel cells that can also directly consume fossil fuels like methane or other hydrocarbons, and even carbon monoxide. Such fuel cells, they often have a higher temperature because they need to reform the hydrocarbons into hydrogen and carbon dioxide. It's interesting to know that NASA uses alkali fuel cells to produce electricity and drinking water at the same time. So the water that is produced by combining the hydrogen with the oxygen is then used for the astronauts as drinking water. Let's focus on the proton exchange membrane fuel cells. They are most important for vehicle applications. The reason for that is that they run at a low temperature, and this enables a quick startup. High temperature fuel cells are more for power plant type operations because they need some time until the temperature is reached, that they can reach the output. Proton exchange membrane fuel cells are also better when it comes to changing the output, which is important for applications like electrical vehicles. Here you see a schematic of the stack of a proton exchange membrane fuel cell. In the center, of course, we have the membrane that allows protons through but prevents the gases from meeting directly. That ensures that we have the electron transfer through the load instead of directly inside the fuel cell. The membrane is sandwiched by the electrodes. They contain catalyst nanoparticles that help the reactions at the electrodes. Then comes a diffusion media on either side that distributes the gas flow homogeneously across the porous electrodes. And finally, on the outside, we have the gas flow plates. They are made from graphite. Graphite is electrically conductive, so they serve as contacts, but they also serve to bring in the gas and distribute it across the electrode surfaces. And graphite is a fairly rigid material, so they also serve as mechanical support that holds the entire fuel cell together. Let's see how a proton exchange membrane works. They were developed by DuPont and are sold under the trade name Nafion. These membranes are made from a polymer that has a hydrophobic backbone and hydrophilic side groups. The hydrophilic and the hydrophobic parts of this polymer, they repel each other. And so if we put this polymer in solution, then structures like this form, where the hydrophobic backbones stick together and the hydrophilic side groups try to be close to each other. And if things are done right, this turns into tubes that permeate the entire structure. Now, because we have hydrophilic molecular tails on the inside, these tubes attract water into themselves. Once water is in there, these tubes can act as ion channels, and that gives these membranes their proton transporting properties. Since they only work when water is inside these pores, these membranes cannot be used in high temperature fuel cells, otherwise the water would evaporate. Here you see a schematic of the catalyst electrodes that are used in proton exchange membrane fuel cells. These electrodes are porous to permit the gas to the membrane and into the electrodes. They are made from carbon micron-sized particles. That gives these membranes a large surface area where they can interact with the gas. The carbon structure is infused with platinum nanoparticles and with Nafion to create a continuous phase with the proton exchange membrane. That makes the proton transfer more efficient across the fuel cell. The carbon particles are conductive, and that creates a natural charge transfer path to the contacts of the fuel cell. Price is an important consideration when it comes to feasibility of proton exchange membrane fuel cells. This graph shows the development of the price starting in 2002, ending in 2010, and a projection up to 2015. And so we see that in 2010 the price per kilowatt was $51. The projection for 2015 is $30 per kilowatt. So if we have a typical car that needs about 100 kilowatts in fuel cell output, the cost will be somewhere between $5,000 and $3,000. That is pretty similar to batteries that are used in plug-in electrical cars that have a modest driving range. Other issues with regard to a widespread use of fuel cells are, of course, hydrogen production. Right now, most hydrogen comes from methane reforming. That means that fuel cell cars mainly run on fossil fuel. As long as hydrogen is not generated via electrolysis and renewable electricity, the advantages of cars powered by fuel cells are limited. Other challenges are hydrogen storage. There is currently no good storage technique out there that would allow to store a significant amount of hydrogen in a small space or with a low weight. And of course, as discussed earlier, the low efficiency of current fuel cell designs is also an issue, because combined with sustainable hydrogen production, only less than 30% of the energy makes it really into the motor of an electric car. This is how currently hydrogen is being produced: methane steam reforming. And as the name says, hot steam is used together with methane to convert the methane into carbon monoxide and hydrogen. This is followed by the water gas shift reaction, which is then an exothermal process. This maximizes the hydrogen component of the gas that is coming out of this reaction. The methane steam reforming process can be about 70% energy efficient. So if we combine that with a 40% fuel cell, a fossil fuel to electricity efficiency of about 28% can be achieved. You saw this graph before. This graph shows the energy density of a number of fuels. And we have here on the x-axis the energy per kilogram, and on the y-axis we have the energy per volume. And so you see here that the lithium-ion battery is very much at the origin. That means it has a very low energy density in volume or weight. When we go to hydrogen, we see that we have an incredible energy density per weight. Hydrogen is the fuel with the highest energy density per weight. However, when it comes to the energy density per volume, we see here that we are, with the gas, very close to the lithium-ion battery, or worse. And when we compress it to 700 bar, that is 700 times atmospheric pressure, then we just get slightly above. And if we liquefy it, we still didn't go very far. If we compare it with gasoline or even ethanol, hydrogen is much worse in its energy density per volume. The reason for that is that hydrogen molecules do not interact much with each other, in difference to gasoline or diesel or ethanol, where the molecules attract each other via van der Waals forces or hydrogen bonding, so that helps to keep them close together in a small space. Hydrogen, on the other hand, one has to invest energy to compress it or bring it closer together by cooling it down. And therefore, it is very difficult to take a large amount of hydrogen along in a reasonably small space. Let's focus on hydrogen storage. Hydrogen storage is one of the biggest roadblocks right now to large-scale hydrogen use in vehicles. This graph shows various storage technologies that are available right now in comparison with regards to their volumetric capacity and their gravimetric capacity. Volumetric capacity is how many grams of hydrogen can we put in a liter. So you see here that most of these techniques are at 20 to 40 grams per liter. The gravimetric capacity takes the storage container and everything into account that is needed to store the hydrogen, and you see that we are in the single digits. In the case of compressed hydrogen, which is a reliable storage technology that is in widespread use, if we go to 700 bar, then we only achieve about 3 to 4% gravimetric capacity in the storage container. That means that 96 or 97% of the weight of the entire container, together with the hydrogen, is devoted to the container. And the reason for that is, of course, 700 bar is a high pressure, and so we need a very heavy steel pressurizable container to hold the hydrogen in there. Other ways to store hydrogen are by cooling it down. So liquid hydrogen, there we get a gravimetric capacity of 6 to 7%. The reason for that is simply that hydrogen has a very low density, even if it is liquid. Again, that comes from the lack of attraction between the hydrogen molecules. A way to reduce the volume of hydrogen is by bonding the hydrogen to a host matrix that is inside the container. Gasoline is a prime example of this approach because it has a hydrogen content that is 64% higher than in pure liquid hydrogen despite its additional carbon content. This feat is achieved by gasoline because the hydrogen and the carbon form larger molecular assemblies which are attracted to each other via van der Waals forces, which reduces the volume. There is a lot of research going on where this approach is tried to be copied by using porous host materials that have an affinity for hydrogen. And on this graph you see a few of these technologies that are currently being developed. Complex hydride, chemical hydride, C-sorbent, these are technologies where the hydrogen is being bonded to a host material. The goal of this type of research is to find a compromise between being able to release the hydrogen easily while also increasing the density of the stored hydrogen. In gasoline, the release of the hydrogen is an issue because we essentially have to burn the gasoline if we want to make use of its energy. This comes from the fact that in gasoline the hydrogen is bonded through chemical bonds. In these new storage materials, one tries to find systems where the bond between the hydrogen and the host material is weaker, so that by a slight temperature increase, for example, the hydrogen could be released from the storage tank. Let's consider first the physical storage technologies by compressing and cooling down hydrogen. In this graph, the volumetric hydrogen density in kilogram per cubic meter, that's the same like gram per liter, is plotted versus the pressure in bar, so in multiples of the atmospheric pressure. The red curve is followed by hydrogen gas as we compress it. So if we would apply a pressure of 1000 bar, then we would get about 40 kilograms into a cubic meter, or 4 grams into a liter. If we did that, we would need to use a steel vessel that has a ratio of about 1 to 10 between the diameter and the wall thickness. This is this scale over here. So if we go to higher pressures, if we would want to use 2000 bar, for example, we would need a steel container where the wall thickness is 18% of the diameter. So you see, very rapidly we get to very massive steel containers in order to keep the hydrogen under this high pressure. It is not very practical to go to very high pressures and thereby trying to increase the hydrogen density in the tank. Also, you see that the curve is leveling off as we do that, because the closer we press the hydrogen molecules together, the greater we have to work against their repulsion. Now, the blue curve is, for comparison, the volumetric density that could be achieved by liquefying hydrogen by cooling it down to its condensation temperature. And that means we would have to go as low as 21.2 Kelvin, that is minus 251.95 centigrades. So this is pretty close to the absolute zero, and you can imagine that this takes a lot of energy. If one uses the so-called Linde cycle, which is the standard technology to cool down gases, it can be calculated that about 50% of the lower heating value of the liquefied amount of hydrogen would need to be used in order to cool it down. So by storing it at low temperatures, we would lose about 50% of the energy of the gas that we're storing. That is not very effective. This means that we either lose a lot of energy by cooling it down, or we have to have a very heavy tank, and actually it also costs energy, of course, to compress the hydrogen. And so all this doesn't look very good, and it is not very practical for a widespread application and use of hydrogen gas as energy storage. The next few slides will be about solid-state storage. Here we exploit the idea that the volume of hydrogen can be reduced if we bond it to a surface. The materials that are currently being investigated, they all have in common that they don't really react with the hydrogen, so it's not a situation like in gasoline, but where hydrogen has a high affinity to bind weakly to the surface, so this can be a reversible process. one gets the hydrogen into the pores of the material, and then by heating the material one can force the hydrogen back out. Here's a list of materials that are currently being investigated. So it's pretty much anything that is chemically fairly inert and has pores or a large surface area. So we have activated carbon and carbon nanomaterials. There are metal organic frameworks. These are materials that are self-assembling in solution into porous structures like you see here. Then there are zeolites. These are also materials with a porous structure and a large surface area. Then metal hydrides. These materials consist of metals that have already reacted with hydrogen, but hydrogen still has an affinity to coat surfaces of these materials, and so they can also be used in powder form to create a large surface area absorbent material for hydrogen. Here is an example of these solid-state storage materials, metal organic frameworks. There are two research groups at USF that actively produce these materials and investigate their hydrogen storage capabilities. These are the research groups of Professor Zaworodko and Professor Ma at the chemistry department. These materials self-assemble in solution based on metal oxide corner pieces and carboxylic acid spacers. Based on the length of the spacers and the geometry of the corner pieces, one can form different types of molecular lattices. Once one has the molecular lattice, we can infiltrate hydrogen into the pores and the hydrogen will bond to the structure. This graph also shows the hydrogen uptake of this particular material. You see here that depending on the surface area of the MOF structure, the hydrogen uptake is somewhere between 2 and 8 weight%. If you remember, pressurized hydrogen was somewhere around 3 or 4. This means that these materials are a little bit better. But one has to keep in mind that the temperature at which these values were achieved was at 77 Kelvin, that is liquid nitrogen temperature, that translates into minus 196 centigrades. So there is still a considerable amount of energy that goes into cooling down the gas and the storage container to achieve this type of uptake. Let's have a look at the Honda Clarity hydrogen vehicle. It's one of the very few mass production ready hydrogen cars. Its main energy source is a fuel cell and a hydrogen tank, but there's also a lithium-ion battery to help with the regenerative braking and short-term energy needs. This car can only be leased right now. There are only a few refueling stations around Irvine in Southern California, and the monthly lease is $600. As you would expect, the filler is a gas line fitting. The Honda Clarity has a standard pressurized steel tank, and they chose to go at about 344 bar. That allows to store 23 kilogram per cubic meter in this tank. The tank size is 171 liters. This means that we can put 3.9 kilograms of hydrogen in there. That gives us a range of 240 miles or 384 kilometers. So this would imply that we can do 98 kilometers per kilogram. The Honda website states 96. So that's about 60 miles per kilogram. Now the hydrogen energy density is about 3 times that of gasoline per weight. So we can convert this number into miles per gallon, and so we end up at 76 miles per gallon equivalent mileage. Now if we assume that the hydrogen is produced by steam reforming SMR from methane at 70% energy efficiency, the mileage would compare to about 53.2 miles per gallon. So we can compare that with other cars. The 4-cylinder Honda Accord does, for example, 25 miles per gallon, and the Prius clocks in at about 45 to 50 miles to the gallon. So you see that the Prius and the Clarity are pretty similar in their equivalent mileages. And of course this makes sense because we are still driving with fossil fuel. We simply convert it and then use a slightly more efficient powertrain with regenerative braking. That makes it better than the standard Honda Accord, but the Prius also uses regenerative braking, and therefore there is not that much difference between the Prius and the Clarity, no matter what fuel they use. You may remember in 2010 the so-called Bloom Box made headlines when it was featured on 60 Minutes. The Bloom Box is a solid oxide fuel cell which uses methane directly, and the methane is steam reformed inside this fuel cell to hydrogen using the water that is produced in the fuel cell electricity generation process. One advantage is that since this is a high temperature fuel cell, no platinum is necessary for the reactions as catalyst. Here's a rendering how these fuel cells could be deployed. They are modular and they connect directly to a natural gas line and put out AC quality power. Let's have a look at the datasheet of the Bloom Box. The manufacturer touts this product as a way to reduce carbon dioxide emissions and that it would put out green power. So let's see what we have here. They state that the generation efficiency is larger than 50% and that the carbon dioxide emissions are 773 pounds per megawatt hour. They say that this represents a 34% reduction versus thermal gas-based generation. So these are regular gas-fired power plants. So I looked up at the Energy Information Administration what the current state of the art for gas-fired power plants is, and it turns out that their efficiency is 48% on average, and that their carbon dioxide emissions are 1100 pounds per megawatt hour. So when we compare these two numbers, it really seems there is a 30% reduction. However, there is the problem that the efficiencies are similar. When they write larger than 50%, then it's probably 50.1% or so, pretty close to 50%, and the efficiency of the gas-fired turbine is 48% on average. So since both run on methane as original energy source, one would expect that the carbon dioxide emissions are similar, because the end product in both cases is water and carbon dioxide. So something appears to be a little bit strange here with these numbers. When one looks at the cost, there are lots of numbers thrown around on the internet, and some of the more serious studies claim that the cost is about $10,000 to $14,500 per kilowatt installed. That compares to $500 to $1,000 in gas-fired power plants, so we have easily a factor 10 between the Bloom Box and the standard technology. The price per kilowatt, if one takes into account the posted maintenance costs of Bloom Boxes, one can calculate that it is about 30 cents per kilowatt hour. This compares to about half or less, depending on where you are in the United States, for regular power plants. So all this put together seems that the real benefit of the Bloom Boxes may be that they are modular and decentralized. Therefore, one can use them perhaps to produce more stable power in comparison to the electrical grid, where power outages occur relatively frequently. At the end of part 2 of the energy storage segment, I want to discuss flow batteries. Flow batteries operate somewhere between fuel cells and regular batteries. What they have in common with fuel cells is that their capacity is virtually unlimited. It's only limited by the size of the electrolyte tanks that are hooked up to the positive and negative half cells of these batteries. They also have a proton membrane that allows the exchange of protons between the two sides but keeps the electrolytes separate. So in this battery, the high and low energy states are created by having less and more positively charged ions on either side. The most popular flow batteries are made with vanadium electrolytes. The charge state of vanadium ions in electrolytes ranges from 2+ to 5+, and this is used here in these vanadium flow batteries. On the positive half cell of the flow battery, we use an electrolyte where the vanadium ions are between 4 plus and 5 plus charged. And on the negative half cell we use vanadium ions that are between 2 plus and 3 plus. So if you think of an electron that would hop on a vanadium ion, it has a higher energy on the less positively charged vanadium ions than on the more positively charged vanadium ions. Because of this higher positive charge, the electron is attracted more strongly, and so it loses more energy when it goes on these ions in comparison to these. So in our battery scheme of high and low energy states, the less positively charged ions form the high energy state and the more positively charged ions form the low energy state. The battery now operates by shuffling electrons from the less positive ions to the more positive ions, that is discharging, and charging of the battery is to bring the electrons back to the less positively charged vanadium ions. So you see that here in this figure. Electrons are pushed onto the electrode in the negative half cell during the charging process, and they hop on the vanadium ions and they convert the 3 plus ions into 2 plus ions, because one positive charge in the nucleus of these ions is now compensated with this electron that just came in during the charging process. On the other side, electrons leave the positive half cell, and that causes the formerly 4 plus charged vanadium ions to be now 5 plus charged. When the battery is charged, we have 5 plus vanadium on this side and 2 plus vanadium on that side. Now in this process, of course, electrons left here and they showed up on this side. That means that this side got negatively charged relative to this side. This is compensated by allowing protons to go from this side of the electrolyte to the other side. So we have a proton transfer through the membrane during the charging process. Now, once we hook up a load to the two electrodes, the opposite occurs. Electrons leave on this side, so the vanadium ions go from 2 plus to back to 3 plus. Protons go over to the positive side, and here the electrons arrive once they make it through the load, and the 5 plus vanadiums go back to the 4 plus state. So the energy that we can store in this battery simply depends on the number of vanadium ions we have on both sides, and that is of course proportional to the amount of electrolyte that we have. So the tank size limits the energy that can be stored in this battery. The power, on the other hand, of course, remember, power is energy per time that can be dispensed from a battery. That power is of course limited by the size of this mechanism. If we have larger electrodes and a larger membrane, then we can bring over more protons per time, and we can also put more electrons onto the ions per time. Therefore, the size of the cell determines the power of such a battery.
This concludes part 2 of the energy storage segment. Thanks for watching.